Hello and welcome to Power System Analysis 2. We'll be talking about Gauss-Seidel method here. Okay, so it is we have already talked about the ways of load. How the equations are being formed in the load flow analysis. So Gauss-Seidel method is one of the method where it's very easy and very basic method of power system analysis and load flow analysis. So we'll be looking for Gauss-Seidel. Okay, now the Gauss-Seidel method is an iterative algorithm. What is iterative? That is that we do not know you cannot find the direct solution of it. So what we do, we give a guess solution, and then we see whether the solution matches the equation or not. If it do not match, then we'll give some other just modify it, and again we give the solution. So it goes on in a cycle. It's called an iteration. So it is an iterative algorithm for solving set of non-linear algebraic equation. Our equation is obviously it is non-linear. So to start with, a solution vector is assumed. We assume a solution vector. Why we are talking about a vector? Because we are getting the value of multiple buses. So when we are getting the answer for multiple buses, we have seen that it can be formed in a form of a matrix. So the answer will come not as a single answer, but a series of answers for all the different buses. So this series of answer will be in terms of, we can term it as a vector. That is, it is a series, an array of answers. So we assume a solution vector or array based on the guidance from practical experience or physical situation. Now, why this practical experience and physical situation is mentioned is that if we give the solution a random value, okay, that value may not converge. Like if for example, just imagine an answer of an equation is, let's say, 5. Okay, so if you go around, say you expect, okay, this equation might come around 5 or 6, so you give 4.9, 4.8. So it will slowly, you will see this thing will converge, and you will get the answer very easy, fast. Now if I, let's say I give a value of 100, okay, so the equation will give wrong answer, and the error will be very large, and you may be tempted to go, okay, if 100 is not working, so let us take 150, let us take 200. So you are going past the actual answer. So this is the reason we have to use some value, that is, we know this value will work. Now for this value you need some practical experience. You should know that for these buses should be the amount of voltage, or the voltage angle will be something around this. So you place that for those values. It may not be correct, but it should be close to it. So one of the equation is then used to obtain the revised value of the particular variable by substituting it in the present values of the remaining variable. Now you go and substitute that value. The solution vector immediately updated and in a respect to this variable. So you get the solution vector. Okay, the process is then repeated for all the variables, and thereby completing one iteration. So you use one value, you get solve for one bus, and you go on solving for all the buses. So you get a solution vector. So you have inject your input is a solution vector, and you get an updated answer vector. Okay, so the iterative process is then repeated till the solution vector converges within a prescribed accuracy. Okay, so what is the accuracy? For example, just I need you to understand this. The iterative way is like, let's say you get an equation like x plus y equal to 5. Okay, now there are multiple combinations. Okay, so you give you say, let's say x is 3, y is 2. Okay, that so, or it maybe it may not be some simple like that. For let's say equal to x plus sine y equal to sine y square equal to something equal to x into sine y plus z equal to 0. So you expect some value, so you put the value, you get x equal to some value, y equal to some value, z equal to some value. Now you see that you put the equation, it is not coming 0. Okay, then now you change the x, change the y, change the z, it is coming close to 0. So then you go on changing and you see the value is coming very close to 0 but not actually 0. Now at that certain point you say it's okay, now we can expect this this to be a solution. That means you have some tolerance limit, that if the value is very close to this value, I am okay with it. So this tolerance limit is basically the actual answer minus the what your answer you are getting. So you have to keep at this tolerance level, and when the tolerance limit is reached, the iteration is stopped. Okay, so the convergence is quite sensitive to starting values assumed. We have already talked, like if you start with 100 where the actual value is 5, then it might not converge. Now fortunately, in a load flow analysis, a starting vector close to the final solution can be easily identified from previous experience. Okay, so to explain how Gauss-Seidel method is applied to obtain the load flow solution, let us be assume that all buses other than the slack buses are PQ buses. Now we are talking only PQ bus and the slack bus. We need a slack bus because we are doing a load flow analysis. Basically it is nothing but a node voltage analysis, and we need one bus or one node to be a reference bus. That node is nothing but the slack bus for our cases. Now for the other buses, we assume those buses to be PQ buses. Now we shall see later that the method can be easily adapted to include PV buses. Okay, now the slack bus being specified, there are n-1 bus voltage starting values whose magnitude and angles are to be assumed. Okay, now for the, let's say there are n number of buses, one bus is slack bus. Slack bus is where the voltage and the angles are specified, but P and Q is not specified. Now the other buses other than the slack bus, how many buses are there? n-1 buses are there. Okay, now if we assume that n-1 buses are PQ buses, then in the PQ buses P and Q are mentioned, but not V and delta are not mentioned. So we have to assume those values of VL delta. So how many VL delta we have to assume? n-1 V delta values you have to assume, and these values are then updated through the iterative processes. Okay, now we'll go to the Gauss-Seidel method. Now the first, the voltage at the ith bus is obtained as follows. Now the first equation, Ji equal to Pi minus J Qi divided by V star I. This is obtained from the previous equation. You can see that V star I is nothing but P minus JQ. Remember, V star I is equal to P minus JQ. Vi star is equal to P plus JQ. But we are taking star or conjugate of V, but not the I. So when we say Ji, that is the injected current in ith bus. Injected current, that is the current, that is actual current that is getting in the ith bus, is nothing but is equal to injected real power minus J of injected reactive power divided by the voltage at that bus and the conjugate of the voltage of the bus. Now if you go to the second equation, Vi equal to 1 by Yii equal to Ji into J1 minus sigma of Yik into Vk. This is again obtained from the previous equation where we had talked about the primitive networks. Okay, now here we can replace this Ji by the P minus Jq divided by V star. So this equation Vi equal to 1 by Yii into Pi minus Jqi by V star I is equal to Yik into Vk. This is actually what you are going to solve for the Gauss-Seidel analysis. Okay. Now, if you notice here, Vi is present in both on the left hand side as well as the right hand side. On the left hand side we have single Vi, and on the right hand side you have the Pi minus Jqi divided by Vi star. When we assume a V, okay, now we are talking about the PQ bus. What are we assuming? V and delta. Okay, now these V are in terms of complex numbers, so delta is already there. This Vi is nothing but modulus of Vi into angle delta, an angle delta. Remember that. So both V and delta, what we have assumed, will be on the right hand side. Okay, now when we put the value, the assumed value of this V and delta, we will get a new value of V and delta on the left hand side. Okay, now we are going to check the V and delta and we will see whether that matches. So we can say the voltage substituted on the right hand side of the equation are most recently calculated and updated values for the corresponding buses. So whatever the most recent one, what is the most recent one? First we need to assume. So assume V and delta we put on the right hand side, we will get a new one on the left hand side. Then again we put that new one back to the right hand side, again you get a second updated new one on the left hand side, and this cycle goes on and goes on and on till an accuracy is reached. The voltage substituted on the right hand side of the equation are mostly recently calculated or updated values for the corresponding buses. During each iteration, voltage buses 1, 2, 3 are sequentially updated. So remember, this is Vi. Now if there are n buses, how many equations to be solved? N minus 1, because slack bus we are not considering. Okay. Now voltage for the ith bus we have already seen. This is how the ith bus is given. Okay. Now V1, the slack bus voltage being fixed, is not required to be updated. So that is not required. We have already told that the iterations are repeated till no bus voltage magnitude change by more than the prescribed value during an iteration. That means what? Every time we go on updating and updating and updating, the values of the voltages at different buses do not change much. Okay. So let's say, moreover, let me be clear that all these voltages are in per unit. So we start with a voltage of 1 per unit. So we get, let's say for bus number say 15, you get the value of 0.15, let's say 0.9, then you get 0.95, then again you get 0.951, then you again get 0.945. So now you will get the value of the buses is not changing much. So around this value is you can be sure that this is the value. Okay, so this is how we do it. During each iteration, voltage buses I of 2, 3 to n are sequentially updated. V1, the slack bus voltage being fixed, not required to be updated. Iterations are repeated till no bus voltage magnitude change more than the prescribed value during iteration. The computation process is then said to converge to a solution. This process is called this Gauss-Seidel iterative method. It is much slower to converge and sometimes fail to do so. It is the basic and very slow to converge, but this is where we start. The other methods we will go on discussing. The Newton-Raphson method. I think you have heard of Newton-Raphson method previously. Newton-Raphson method, fast decoupled load flow. Okay, so these are all based on the Gauss-Seidel method, the much more updated, modified thing. But this is the core. But it is again very slow. So we'll talk about the algorithm. First, step 1, with the load profile known for each bus, the PDI and QDI is known. What is the load profile? It is that for every bus, what is the load connected to that bus? So load, we are talking about load, so it becomes the real load and the reactive load. The real power load is PDI, reactive power load is QDI. Now we allocate PGI and QGI for all generating stations. While active and reactive generations are allocated onto the slack bus, these are permitted to vary during the iterative computations. Okay, now slack bus P and Q are given. The values of P and Q in the slack bus do not have the value of P and Q. Now we assume a value of P and Q for the slack bus, and then we do the calculation, and it is permitted to change. Okay, this is necessary as the voltage magnitude and the angle specified at this bus, it is that we cannot change that voltage and angle, so we have to change P and Q for slack bus. So with this step, bus injection Pi plus JQI are known for all buses that other than the slack bus. So we at this step, the load is known. You have to say that this is the generation for every buses. Okay, that means when load is known, you have to, when the bus is connected to if there is a generation in the bus, you have to consider that, so that we can get the total Pi plus JQI, that is the total real and reactive power injection. What is the real and reactive power injection? It is Pi is equal to PGI minus PDI, that is the injected power is equal to generated power minus the load power. Okay, so Pi is equal to PGI minus PDI, QI is equal to QGI minus QDI. Now you go to step 2, the assembly of the bus admittance matrix. So we have to, that is why we have to learn how to calculate the bus admittance matrix. Now we need to form the bus admittance matrix. So the assembly of bus admittance matrix Y bus with the line and the shunt admittance data stored in the computer. Y bus is assembled using the rule of self and mutual admittance. So we have done this kind of process. Alternatively, Y bus is assumed where input data are in the form of primitive Y matrix and the singular connection A matrix. Okay, now this is nothing, that it says that you need to form the Y bus. If it Y bus is given, it is okay, then, or you have to form it from the primitive. Sometimes the primitive matrix is given, then you have to form the Y bus. We already know how to do that. Remember, all the diagonal elements are sum of the admittance at that bus, and off diagonal elements are the negative of the connections between the two. Okay, you just go through the previous classes. Now we go to the step 3, iterative computation of bus voltages for voltages 2 to n. 1 is already known because 1 is a slack bus. To start iteration, let us set up initial voltages as assumed. Since in a power system the voltage spread is not too wide, it is normal practice to use flat voltage start. That means we assumed all the voltage to be 1 J0, that is 1 angle 0. Okay. Now it should be noted that n-1 equations in complex numbers to be solved iteratively for the voltage of V2, V3, Vn. All the voltages are all in the form of Cartesian coordinate like EI plus JFI, or you can do it in the polar coordinates, V magnitude V e to the power of J theta 1. Okay. So we now this AI, whatever you can this AI can be computed. These AI are the you can see this this AI, that is Pi minus JQi divided by Yii. These are the part of the equation. So you have to, sorry. So you can see they are part of the equation. This Pi minus JQi divided by Yii. Okay. So these are all part of the equation that needs to form. So you so rather than finding the entire equation together, we find first AI. AI is a part of that equation, and similarly BI is that another part of the equation, so that that equation can be simplified in the form given on the left hand side, on the right hand side. The iterative process is continued till the change in the magnitude of the bus voltage delta Vi to the power is the on the iteration of r plus 1 between two consecutive iteration is less than certain tolerance of bus voltage. Now from in this position, let me tell you about the sign conventions. Now you can see some value is on the subscript and some value is on the superscript. The superscript value are in small bracket. The small bracket superscript is not the power. It says the number of time iteration is done. Okay, you go to the, if you can see the right hand side equation, you see V r plus 1 equal to AI by V r. That means what? When you put the when you go to the rth iteration, first iteration, second iteration, third iteration value, if you put, you will get third plus 1 on the left hand side. So this r plus 1 says that it is the updated iteration. So to the power this bracket, it tells you the number of iterations. Okay, and the subscript, it says that which bus we are concerned with. Now this modulus of V iteration of r plus 1, modulus of delta V on the r plus 1, which is on the first point. Okay, this is the change of the voltage of the ith bus after r plus 1 iteration. After r plus 1 iteration, if you see the difference of r plus 1 iteration and rth iteration is within a certain limit, that is, let's say you get one value at, let's say, 20th iteration you are getting a value of 0.9. 21st iteration you are going 0.91. So you are getting a 0.01 difference. You are saying it's okay. 0.01 difference doesn't make any difference. So I am okay with 0.9 or 0.91. This is the final value. That is what it is telling about. Okay. Now after you have done that, we got the values of V. Now you have to compute the slack bus power, because slack bus power is not known. Slack bus voltage and delta is known. So you substitute all buses in step 3 along with V to yield the power, active power of Si plus Si star equal to Pi minus JQi. Okay. Now we go for the computations of line flow. This is the last step. This is the last step in the load flow analysis, where the power flows on the various lines of the network are computed. Consider the line connection between bus I and bus K. So I have given the diagram from bus I and bus K. The line and transformers at each end can be represented by a circuit which is series admittance and two shunt admittances. So if you go and see the circuit, how the circuit is being laid out, so it might have a series and shunt admittances. Okay, so from this we needed to write the current equation. Hopefully you are getting the current equation. That is IK you look at IIK, that is the current coming out of bus 1, is divided into IIK1 and IIK0. That is what it is written. That is nothing but Vi minus Vk into Yik, okay, and plus Vi into Yik0. So the power that is fed between line I to line K, it is Sik, that is Pik plus Jqik, and that is given as Vi into Iik. So if I say what is the power that is flowing from bus I to bus K, it is Vik, that is the voltage at bus I, into Iik star. Okay, so this is how we write the equation. So the total transmission loss can be computed with Sik and plus Ski. So when you see Sik and when you see Ski, there should be some losses. Okay, that loss, so the power that is going out from Sik is not reaching S voltage at the bus K. Some of it is lost. So that is how we are going to find out the loss of power. Okay, now there is a new concept called the acceleration of convergence. Now convergence in the Gauss-Seidel method can sometimes be sped up by the use of acceleration factor. If you go and have a experience for the Gauss-Seidel method, it takes a long time, hundreds of iterations, then you will get the answer. So for the ith bus, the acceleration value of the r plus 1 iteration is given by an alpha, where alpha is a real number called the acceleration factor. A suitable value of alpha for any system can be obtained by trial load flow studies. The recommended value of alpha is 1.6. A wrong choice of alpha can lead to a slow conversion or even into a divergence. Now this alpha is nothing but that is to be multiplied with the updated value. Okay. Now one more changes we are talking about is the PV buses. We have talked about the PQ buses. Now what will happen if you have a PV bus? Now if PV bus, if you remember, PV bus has a real power and a voltage. And voltage delta and the reactive power injection is not being mentioned. So P and V are specified, Q and delta are unknowns to be determined. Therefore, the values of Q and delta are to be updated at every iteration through appropriate bus equation. Okay, so here if you see P and V and are defined, so we cannot compute the V here. Okay, so here you have to compute the delta and the Q. So we have to continuously use the same voltage, but the delta will be changed. This is accomplished with the following step for the ith PV bus. See, now what we do, we find the Qi. Qi, how are you finding out? It is the imaginary part of V star I. Now here I is replaced by sigma of Yik into Vk. That is sigma of all the currents that in going out from I to different voltage buses. So this revised value of Qi is obtained from the above equation by substituting most updated values of the voltage on the right hand side. In fact, for the r plus 1th iteration, one can write the above equation as it is updated. This is the new, you go for the new voltage value, updated voltage value, and you will get an updated Qi. Okay, from those Q, we will get a revised value of delta. Now delta will be obtained by finding the angle of the equation that was previously given in the Gauss-Seidel equation. Okay, this is the only difference in the PV buses. So the PQ buses we have seen, just for the PV buses the Q is to be found out and delta is to be found out. Now, as explained already, the physical limitation of P generation require that P demand at any bus must be in the range of Q min and Q max. So you cannot have a random value of Q. If at any stage during the computation Q at any bus goes outside limit, it is fixed at Q min or Q max. Let's say we say 100 MVR is the limit. So we got the answer of 200 MVR. We will not take that value, rather we will consider only 100 MVR and go for the next iteration. Okay. Now this is what we have talked about, that if the Qi of r plus 1th iteration is less than Qi mean, then set Qi r plus 1 as Qi mean, that we have talked about. That if it goes beyond the limit, we will put the limiting value only. Okay, so this is what basically we find out, and then we find out Q and delta. Now this is the flow chart. Question might ask me to write the flow chart. So this is what the flow chart you have to find out. So just go through the flow chart. Hopefully that you can understand this. So you have to find the primitive matrix, bus incidence matrix, slack bus you have to set, all the real powers, reactive powers you have to set. Okay, then you have to compute the latest, you have to assume a latest V and delta, then you compute the latest V and delta. Okay, and then you have to test that whether this is the test part is for the PV bus, whether it is a PQ bus or a PV bus. So if it is a PV bus, then you have to check whether the Q is going outside the range of Q or not. Okay, then you have to calculate. So just go through it, because what I have said previously, this is that is being discussed in the in this flowchart format. Okay, so this is the end of the slide. If you have any doubts, please contact me. Thank you.